Every engine we have ever built points one direction, forward. At light speed, 186,000 miles per second, time folds. Fuel math breaks. The universe ahead turns into a wall of radiation. We will walk through the physics that makes return impossible, the real engineering proposals that quietly admit it, and the one scenario where a crew might survive the trip back. If you want to understand where humanity's ambition actually ends, subscribe and stay with us. Prepare yourselves. We begin. You are sitting in the crew briefing room. The mission clock reads 0, and someone just slid a document across the table that nobody wants to read out loud. It is the return fuel calculation. For most of human history, every journey had a matching return. You go out, you come back. Ships cross oceans, planes cross continents. Even our deep space probes, we knew they were one way, but we told ourselves that was a technology problem, a budget problem, something we would solve later. Light speed feels different. Light speed feels like the finish line. It is the trap. The moment you frame light speed as a destination, you stop asking the question that engineers ask first: how do we get the crew home? And when you finally do ask it, the answer comes back the same way every time. You do not. Here is why. Reaching light speed, or even a meaningful fraction of it, requires an almost unimaginable amount of energy pushing the ship forward. Physics does not offer a discount on the return trip. Every mile per hour you gained on the way out has to be paid for again on the way back. The fuel you burned accelerating is gone. You arrive at your destination, wherever that is, with an empty tank and a universe between you and Earth that your ship cannot cross again. Engineers call this the symmetry problem. The mission is not one leg, it is two. Every proposal that focuses only on the outbound journey is technically a suicide mission with better branding. The breakthrough Starshot project, backed by serious physicists and serious money, proposed laser-pushed sails that could reach 20% of light speed. 20%, a fraction of the full number, and already the return problem defeated them. Their own documentation acknowledged it. The sail arrives at the destination system in roughly 20 years. It has no deceleration system. It has no return propulsion. It flies through at 20% of light speed and keeps going into the dark beyond. That is the state of our most funded, most serious proposal. Now scale that up. Imagine a ship not at 20%, but pushing toward the full number. The energy required does not scale up in a straight line. It curves, steeply. Each additional percent of light speed demands exponentially more fuel, more power, more everything. The rocket equation, written down in 1897 by a Russian schoolteacher named Konstantin Tsiolkovsky, describes exactly how brutal this curve gets. We will go deeper into that math in the next chapter, because what it reveals will reframe everything you thought you knew about propulsion. But stay here for a moment, because the one-way ticket problem is not purely a fuel problem. Every spacecraft humanity has ever built was designed around the assumption that some version of return, or at least continued operation, was possible. Voyager 1, launched in 1977, is now over 14 billion miles from Earth. We can still talk to it. We can still receive its signal. It has not returned, but it has not truly left either. It remains in contact. A lightspeed mission breaks even that thread. Past a certain velocity, the ship's own motion starts outrunning the signals it sends home. The crew becomes unreachable, then invisible. Then, from Earth's perspective, effectively gone before they even arrive anywhere. The mission ends at launch. That is the one-way ticket problem. And the fuel math waiting in the next chapter makes it look almost simple by comparison. Konstantin Tsiolkovsky wrote the equation that governs all of rocketry in 1897. He was a schoolteacher in a small Russian town, mostly deaf, working by lamplight. He had never seen a rocket launch. He derived the math anyway, and it has never been wrong. The equation is elegant. It connects three things: how fast you want to go, how fast your exhaust exits the engine, and how much of your ship's total mass must be fuel. Change any one of those numbers, and the other two respond immediately. At low speeds, the equation is manageable. To reach orbit around Earth, roughly 5 miles per second, a rocket needs to carry a significant amount of fuel, but it is doable. We do it regularly. At higher speeds toward the planets, it gets harder. Engineers compensate by staging. Drop the empty fuel tank, ignite the next engine. Repeat. Every major deep space mission relies on this trick. Now push the speed toward 1% of light speed. 1% sounds almost modest. 1 out of 100. But 1% of light speed is still roughly 1,860 miles per second. To reach that using chemical rockets, the fuel required would outweigh the ship by a factor so large the number stops feeling real. The ship would need to be almost entirely fuel, with a payload so small it could barely carry instruments, let alone a crew. Here is the image that makes it land. Imagine filling an entire ocean with rocket fuel, then using that fuel to push a school bus. You would still fall short of 1% of light speed. This is confirmed physics, not a theory or an estimate. The exhaust velocity of chemical propulsion simply cannot overcome the curve of the equation at these speeds. The ratio of fuel to payload becomes astronomical. Before the speed becomes astronomical, so engineers move to ion drives. Ion engines exhaust particles far faster than chemical combustion does, which helps the equation considerably. They power missions right now, operating in the outer solar system. But ion drives produce tiny thrust. They accelerate slowly over months and years, scaled up to a crude ship trying to reach meaningful fractions of light speed. The power requirements jump into territory that no power source we currently operate can supply. Nuclear propulsion changes the numbers more dramatically. Project Orion, a real engineering study funded by the United States government in the 1950s and 60s, proposed detonating nuclear bombs behind a ship to push it forward. The math worked. The acceleration was real. A large Orion ship could theoretically reach roughly 3% of light speed given enough bombs and enough runway to accelerate. 3%. Still, so far from light speed that the trip to our nearest stellar neighbor, the Alpha Centauri system, would take over 100 years. The crew launching today would never arrive. Their grandchildren might. And the return trip, double the fuel requirement, double the bombs, double everything. The ship that could do it would need to carry so much mass that the equation curves back into impossibility. Every time engineers try to punch through the rocket equation's ceiling, the ceiling rises. The math does not bend. It does not negotiate. It simply states the faster you want to go, the more of your ship must be fuel, until the ship is nearly all fuel and the payload, the people, the mission itself, shrinks toward nothing. The equation Tsiolkovsky wrote by lamplight in 1897 is still winning, but the teams who designed Breakthrough Starshot thought they found a way around it entirely. No onboard fuel, no exhaust, something far stranger. And the reason their solution still ends in a one-way trip is the chapter waiting just ahead. The proposal arrived in 2016 with serious names behind it. Stephen Hawking, Yuri Milner, a coalition of physicists and engineers who had run the numbers and decided the rocket equation was the wrong fight entirely. Their answer was to leave the engine on the ground. Breakthrough Starshot imagined a fleet of tiny spacecraft, each about the size and weight of a postage stamp, attached to a sail made of material thinner than a human hair. On the ground, a massive array of lasers, each one individually weak but combined into a beam of extraordinary power, would fire at the sail. Light carries momentum. Enough light, focused precisely enough, pushes the sail. No fuel on board, no engine to run out. Just a beam of energy crossing the gap between the laser array and the sail for a few minutes of acceleration. The result, according to their calculations, was a sail reaching 20% of light speed in minutes. That is a genuine engineering leap. 20% of light speed means the sail crosses the 4+ light-year gap to the Alpha Centauri system in roughly 20 years. In human timescales, that is a career. A generation, something a mission team could actually plan around. The problem arrives at the destination. The sail hits the Alpha Centauri system at 20% of light speed and has no way to slow down. There is no engine to fire in reverse. The laser array on Earth cannot decelerate it because the beam would have to chase the sail across light years and arrive from the wrong direction. The sail passes through the target system in a matter of hours and continues into the void beyond. Any data it collects must be compressed and transmitted in that brief window. then the sail is gone. Permanently. To be clear, this is confirmed in the project's own design documentation. The team knew this. They designed around it. For an unmanned sail carrying cameras and sensors, a flyby is a scientific mission, disappointing but real. For any version of this concept scaled up to carry humans, a flyby is a death sentence. You arrive, you see your destination for hours, then you fly past it forever. Some engineers proposed a staged sail design, where a portion of the sail separates and uses the laser push from the remaining larger portion to decelerate. The math on this works barely for small unmanned craft. For a crewed ship, the sail area required for deceleration becomes so large that the laser array needed to push it would consume more power than several countries currently produce combined. And the laser array itself presents its own staggering problem. The Starshot team estimated a ground-based array powerful enough for their postage stamp sails would cost roughly $100 billion and take decades to build. Scale that array to decelerate a crewed vessel, and the cost projection stops being a number a single civilization can plan around. There is also the pointing problem. Keeping a laser beam focused on a sail across 4 light-years of space, accounting for atmospheric distortion, stellar gravity bending the beam, and the sail's own drift, requires targeting precision that exceeds anything we have built. The margin for error shrinks as the distance grows. By the time the beam reaches the sail, the window for useful push is measured in fractions of a second. Starshot remains the most serious near-light-speed proposal ever formally studied. Brilliant people spent years on it, and their honest conclusion was a ship that arrives and keeps going. What they never fully solved, and what the next layer of physics makes even harder, is what the universe does to anything moving that fast from the inside out. Because at 20% of light speed, something strange starts happening to time itself. Run the ship at 20% of light speed, and time still moves almost normally on board. A little slower than on Earth, but close enough that you would need precise instruments to measure the gap. Push to 50% and the difference becomes real. For every hour that passes on the ship, roughly 1 hour and 9 minutes passes on Earth. Manageable. Strange, but manageable. Push to 90%. Now for every hour on the ship, over 2 hours pass on Earth. The gap is opening fast. Push to 99% of light speed, and the numbers stop feeling like physics and start feeling like punishment. For every single day the crew experiences aboard the ship, roughly 7 days pass on Earth. For every year the crew lives, 7 years vanish at home. A 10-year mission at 99% of light speed returns, from the crew's perspective, to an Earth where 70 years have gone by. Everyone they knew is dead or elderly. The mission controllers who waved them off are gone. The governments that funded the launch may not exist in the same form. The world they trained for, planned for, and intended to return to has moved on without them in the most absolute way possible. This is confirmed physics. Albert Einstein derived it from special relativity in 1905, and every experiment since has validated it. GPS satellites experience a measurable version of this effect just from their orbital speed. We correct for it in the software. The physics is real. At light speed itself, the equations break. The math produces a result that requires infinite energy to reach, which is why physicists say nothing with mass can reach it. But at 99%, the dilation is already staggering enough to sever any meaningful connection between the crew and the civilization that sent them. Here is the frame that makes it land. Imagine leaving Earth at age 30. You spend 12 years traveling to a star system roughly 12 light years away, decelerating just enough to stop, spending a year studying the system, and then burning everything you have left to come back. From your body's experience, you are 53 years old when you land. From Earth's calendar, over 100 years have passed. Your children, if you had them, are elderly or gone. Your grandchildren are middle-aged strangers. You land into a country that has changed beyond your briefing documents. Your training is obsolete. Your knowledge of Earth's political structures, scientific consensus, even the language itself, may have drifted in ways you cannot predict. The mission did not just cost you the journey, it cost you the world. And this is the scenario where the ship actually makes it back. Most proposals cannot get that far, because slowing down at the far end turns out to be a larger engineering crisis than speeding up was. The deceleration problem is where most near-light speed concepts quietly collapse, and the next chapter is where we walk straight into it. Einstein described it as a thought experiment. Two identical twins, one boards a ship and accelerates to near-light speed, one stays on Earth. When the traveling twin returns, she is younger. Her biological clock ran slower during the journey. Her twin on Earth aged at normal speed the whole time. The paradox part comes from a question that sounds reasonable. From the traveling twin's perspective, was the Earth twin not moving just as fast relative to her? Relative motion works both ways. So why does only one twin age faster? The answer lies in acceleration. The ship twin changed velocity. She sped up, cruised, slowed down, turned around, sped up again, slowed down again. That sequence of accelerations broke the symmetry. The Earth twin experienced none of it. The physical difference in their clocks is real, measurable, and one-directional. The ship twin returns younger, always. For a short trip at modest near-light speeds, the difference is small enough to process emotionally. A few years, a decade maybe. Strange and grief-inducing, but survivable in a human sense. For a real interstellar mission, the numbers grow into something that severs connection entirely. A crew traveling to a star 40 light-years away, at 98% of light speed, would experience roughly 8 years of travel time on the ship. They leave young. They arrive, from their body's perspective, 8 years older. But Earth, during those 8 years of ship time, aged over 40 years. And the return trip costs another 8 ship years, during which Earth ages another 40. The crew lands after 16 years of personal experience. Earth has aged over 80 years without them. A 25-year-old who launched returns as someone who appears to be 41. Earth's calendar reads somewhere around the year 2105. Everyone in mission control is gone. The infrastructure that supported the launch may have changed hands, changed mission, or simply decayed. Scientists have modeled what this kind of return would require psychologically. The crew would need to relearn their own planet. Their expertise, cutting edge at launch, is now 80 years out of date. Every relationship they carried with them has effectively ended, replaced by descendants or strangers. The grief researchers describe it as a form of displacement, so total it has no clean parallel in human experience. Now consider this. The twin paradox assumes the ship comes back at all. The scenarios that produce the most dramatic time differences are the ones where the ship accelerates hardest and longest. Those are also the scenarios where the fuel math is most catastrophic, where the deceleration systems are most inadequate, and where the physical stresses on the hull are most extreme. The faster you go to save time on the journey, the more time you lose on Earth. Every efficiency you gain for the crew compounds the disconnection from home. Some mission planners have argued that this actually removes a psychological burden. If the crew knows ahead of launch that the world they return to will be unrecognizable anyway, then the mission reframes from a round trip into a permanent transfer. You are not going somewhere and coming back. You are going somewhere and staying, then coming home to a civilization that is technically yours, but practically a successor state. That reframe sounds clean on paper. What it cannot account for is deceleration. Specifically, the fact that the physics required to stop the ship at the destination may be beyond any system we can build, and the crew that sacrificed everything to reach their destination may arrive to find they cannot stop in time to land. Every engineer on the team knows it. They write it into the footnotes, they flag it in the risk columns, and then the mission plan moves forward anyway, because stopping is the problem nobody wants to solve in public. Deceleration is harder than acceleration. When you launch, you have a full fuel load, a stationary starting point, and time on your side. You can fire engines in stages, jettison empty tanks, and build speed across years of gradual burn. The rocket equation is brutal, but at least you have the weight of unspent fuel to work with at the beginning. Arriving is the opposite situation. You are moving at an enormous fraction of light speed. You need to shed that velocity completely before you can enter orbit, land, or even do a meaningful survey pass. And you have been burning fuel for the entire outbound journey. Whatever propellant you carried is largely gone. The tank you arrive with is the tank you have left after years of travel, which for any serious near light speed mission is nearly empty. To decelerate using a rocket engine, you have to fire that engine in the direction of travel. Forward thrust that slows you down. This requires the same amount of energy as the original acceleration, applied in reverse. So a mission designed to reach a distant star system needs to carry twice the fuel, once to accelerate and once to brake. Double the fuel means double the starting mass. Double the starting mass means the rocket equation demands even more fuel to accelerate that heavier ship, which means more mass, which means more fuel again. Engineers call this the mass ratio spiral. Each solution makes the original problem larger. Some proposals try to use the destination star's gravity to slow down, a technique called aerobraking when it involves a planet's atmosphere, or gravitational braking when it involves a stellar body's pull. The problem is precision. At near light speed, the corridor for a successful gravitational braking pass is extraordinarily narrow. A miscalculation of even a fraction of a degree at that velocity sends the ship into the star or out into deep space beyond it. The breakthrough starshot design, as discussed, simply removed deceleration from the mission profile entirely. Their sails fly through. That is their honest answer. For crewed missions, the most credible proposals involve something called a magnetic sail, a vast electromagnetic field deployed ahead of the ship that interacts with the interstellar medium and creates drag. Real drag, intentional drag, used to slow the ship. The concept has physics behind it. A team at the University of Washington studied it formally. Their conclusion was that a magnetic sail large enough to stop a crewed ship within a reasonable distance of the destination would need to span hundreds of miles across. Generating and maintaining a field that size requires a power source the mission does not carry. The deceleration problem does not have a clean solution. Every mission that has tried to address it honestly ends up admitting the math does not close. And the ones that do not address it honestly are the ones that bury it in a footnote and keep the mission profile moving. There is one more layer that makes this even worse. The interstellar space the ship must travel through to reach its destination is not empty. And at near light speed, what looks like nothing from the outside becomes something far more dangerous than engineers first assumed. Space looks empty. On a diagram, the path between our solar system and the next star is a clean line through a black void. Engineers who think about interstellar missions know better. The interstellar medium is not empty. It is thin, but it is filled. Gas molecules drifting between stars, charged particles from ancient stellar winds, and dust, microscopic grains of carbon, silicate, and ice, some smaller than a bacterium, some as wide as a human hair, scattered at densities of roughly 1 grain per cubic mile of space. 1 grain per cubic mile sounds negligible, almost nothing. Run the numbers at near light speed, and the word negligible disappears. A ship traveling at 90% of light speed crosses roughly 160 million miles of space every single day. At that speed, the number of dust grains the ship encounters per second rises into the thousands. Each one arrives from the ship's frame of reference like a particle accelerated to near light speed, carrying kinetic energy proportional to its velocity squared. Here is the comparison that makes it land. A dust grain 1/10 of a millimeter across, smaller than a period at the end of a sentence, hitting a surface at 90% of light speed, carries the kinetic energy equivalent to a small explosive charge. A grain the size of a grain of sand delivers energy comparable to a small artillery round. A pebble, if one were encountered, would punch through any material humanity has ever engineered as if it were tissue paper. This is confirmed physics, derived from basic kinetic energy equations. The numbers have been run by multiple independent teams. Nobody disputes them. The question is what you do about it. The first instinct is a shield. Put dense material at the front of the ship. Let the shield absorb impacts and protect the crew behind it. This works at low speeds. At near light speed, the interaction changes character. The dust grain does not simply embed in the shield. At these velocities, it converts. It produces a burst of secondary radiation, X-rays and gamma rays, that penetrate materials that would stop any conventional projectile. The shield that blocks the grain becomes a source of deadly radiation aimed directly at the crew compartment behind it. Researchers studying this problem have proposed a forward-facing cloud of gas or plasma, something to disperse the grains before impact. The physics of this approach require the gas cloud to extend hundreds of miles ahead of the ship. Maintaining that cloud at near light speed requires a continuous energy output that competes with the propulsion system itself. Others proposed electromagnetic deflection, using a charged field to push ionized particles away from the ship's path. This works for charged particles. Neutral dust grains, which represent a large fraction of the interstellar medium, ignore electromagnetic fields entirely. They come through regardless. No material science breakthrough on the horizon solves this. The grains are too small to detect and avoid at any useful range. The ship is moving too fast to maneuver. The physics of impact at near light speed produces effects that conventional shielding cannot counter. Some engineers have proposed accepting a certain casualty rate from micro-impacts and building redundancy into crew compartments. That line appears in actual feasibility studies. The mission plan accounts for crew loss from dust. And then there is the shield solution that does work on paper, an electromagnetic field powerful enough to deflect everything including neutral matter through ionization at range. The field strength required to do that is extraordinary. What it does to the ship and crew inside it is the next problem. And it is almost as bad. The magnetic field idea is elegant in concept. Wrap the ship in a powerful electromagnetic bubble, push charged particles away before they reach the hull, and solve the dust problem without physical armor. Physicists have studied this seriously. The concept goes by several names in the literature, but the core idea is consistent. Generate a field strong enough and wide enough to ionize incoming particles at distance, and then deflect the resulting plasma around the ship. For charged particles like cosmic rays and solar wind equivalents from distant stars, this works. The physics support it. The problem is scale. To provide meaningful protection at near light speed, the field needs to reach out far enough ahead of the ship that particles are deflected with room to spare before reaching the hull. The calculations on minimum effective range produce a bubble that needs to extend several hundred miles in every direction from the ship. Generating a magnetic field that size requires a superconducting coil system. The coils need to carry enormous electrical current without resistance. Superconductivity requires extreme cold. The ship is traveling through the interstellar medium, which is cold enough in theory, but the ship itself is a heat source. Engines, crew, electronics, everything operational generates thermal energy. Maintaining the coil temperature while the ship operates is a thermal engineering problem that compounds every other thermal problem the mission already carries. That is manageable in theory, with enough engineering. The field strength is the harder issue. A magnetic field strong enough to deflect ionized particles at the required range is also strong enough to affect everything else nearby. Every electronic system on the ship operates within that field. Circuit boards, sensors, navigation computers, life support controllers. All of them become vulnerable to field-induced interference at these strengths. Engineers would need to shield every electronic component from the ship's own defensive field, essentially building the ship inside a Faraday cage that is itself inside a magnetic field it cannot fully escape. The crew faces a separate and more immediate problem. Humans are not magnetically neutral. The iron in blood responds to strong fields. Prolonged exposure to the field strengths required for effective protection at near light speed produces documented biological effects, disrupted cell signaling, interference with the electrical activity of the nervous system, potential cardiac arrhythmia in prolonged exposure scenarios. A team of researchers modeled the required field strength against known biological thresholds. Their findings, published and peer-reviewed, concluded that the field required for meaningful protection at 90% of light speed exceeded safe human exposure limits by a factor that would require the crew to be physically isolated from the field source by a shielding layer, that the field itself would partially penetrate anyway. The shield that keeps the dust out puts the crew at measurable biological risk from the inside. Some proposals have suggested a pulsed field approach. Activate the shield only when the navigation system detects incoming particles, then reduce field strength between events. At near light speed, the detection to impact window for a particle is measured in microseconds. No sensor system currently designed can detect, process, and trigger a field activation in that window. The particle arrives before the shield knows it is coming. Every layer of this problem reveals another layer underneath. And the dust and the field problems are only what happens to the outside of the ship. What happens to the signal the ship sends home is a different kind of slow collapse, and it starts before the ship even reaches full speed. The ship launches. Mission Control watches the telemetry. Early in the mission, everything looks normal. Signals travel at light speed in both directions, and the ship is still close enough that the round-trip communication delay is measured in minutes, then hours. Manageable. As the ship accelerates, the delay grows. At 1/10 of light speed, the signal lag reaches a point where real-time conversation is impossible. Mission Control sends a question. The ship receives it hours later. The reply travels back at light speed for hours more. The exchange that took 30 seconds in pre-flight training now takes an entire day. This is the easy part of the problem. As the ship approaches higher fractions of light speed, something more fundamental happens. The ship is moving in the same direction as the signals it sends home. From the ship's transmitter, the signal leaves at light speed relative to the ship. But from Earth's receiver, the ship was already moving away when it sent the signal. The signal and the ship are both heading roughly the same direction, and the ship is moving at a significant fraction of the signal's own speed. The result is that the time between received signals stretches. If the ship sends 1 signal per hour from its own clock, Earth does not receive 1 signal per hour. Earth receives signals at a rate that depends on how fast the ship is receding. At high fractions of light speed, Earth might receive 1 signal for every several hours of Earth time. The information rate drops. The data stream thins. At 90% of light speed, a signal sent every minute from the ship arrives at Earth roughly every 5.5 minutes. This is the Doppler effect applied to light, called redshift, and it does something worse than slow the data rate. It stretches the wavelength of the signal itself. A signal transmitted in the radio frequency range arrives at Earth, shifted toward longer wavelengths. Depending on the speed, the original radio signal might arrive as something the receiving dish was not calibrated to detect. The mission would need to plan for this in advance, building receivers tuned to the expected redshifted frequencies at every phase of the journey. If the acceleration curve changes, the expected frequency changes, and the receiver needs to adapt in real time. Engineers at agencies studying this problem have proposed adaptive receiver arrays that continuously tune to the expected incoming frequency, based on the ship's known velocity. The approach works in simulation. It requires knowing the ship's exact speed at every moment, which requires the ship to transmit its speed data, which is itself part of the signal that is being stretched and degraded. The system that tells Earth what frequency to listen for is transmitted on the frequency that is shifting. Now extend this to the return journey. A ship heading back toward Earth at near light speed sends signals in the direction of travel. Those signals are blue shifted, compressed, arriving at Earth with more energy and at shorter wavelengths than transmitted. This is the opposite distortion. The receiving hardware calibrated for the outbound leg now receives signals at the wrong end of the spectrum. Mission planners would need hardware for both scenarios, maintained and operational, across the full duration of a journey that could span decades of Earth time. And that is all assuming the signal makes it through at all, because the interstellar medium that damages the hull also attenuates signals. Every light year of travel introduces more dispersion, more noise, more degradation to any electromagnetic transmission. The communications picture gets darker the further out you go. But the physics waiting 1 step beyond communication failure is stranger still, because at the speeds we are discussing, the universe ahead of the ship stops looking like the universe entirely. Stand at the front of the ship and look ahead. What you see would not match any star map ever printed. At low speeds, the stars ahead look like stars. At 1% of light speed, the changes are too subtle for the human eye to register without instruments. At 10%, trained observers would notice something. The stars ahead appear slightly bluer, slightly brighter. The stars behind appear slightly redder, slightly dimmer. This is aberration, and Doppler shift acting on visible light. At 50% of light speed, the effect becomes dramatic. The stars that were distributed across your entire forward view begin to cluster toward the center. The sky ahead fills. The sky behind empties. Light that was arriving from the sides of the ship is now arriving more from ahead. because the ship is moving into it. A ring forms, separating the bright forward hemisphere from the increasingly dark rear. At 90% of light speed, the forward sky has collapsed into a brilliant disk of concentrated light. Every star in the universe, from the ship's perspective, appears to have shifted forward. The crew looking ahead sees a blazing concentrated ring of light, everything compressed, everything blue shifted into higher energy. The stars behind are almost invisible. The universe has rearranged itself around the ship's velocity. This is confirmed by relativistic optics equations, the same physics used to model lensing around massive objects. No experiment has run a ship at 90% of light speed to observe it directly, but the equations are derived from the same framework that GPS satellites validate every day with measurable precision. The brightness concentration at the front is not only a visual phenomenon. Higher frequency light carries more energy. The ultraviolet portion of the compressed starlight becomes extreme ultraviolet. The X-ray portion becomes more intense. At high enough speeds, the cosmic microwave background radiation, the faint afterglow of the early universe that permeates all of space, blue shifts into the visible spectrum and then beyond. The ship is flying into radiation that the universe itself generates uniformly, but the ship's speed concentrates it into a beam aimed straight at the hull. This is the relativistic headwind. A ship at 99% of light speed faces a flux of radiation from the forward direction that exceeds what any known shielding material can handle over the timescale of an interstellar journey. The radiation is not coming from a specific source that can be blocked or avoided. It comes from the universe uniformly, transformed by the ship's own speed into a hostile beam. A team at the University of New South Wales modeled the expected radiation dose for a crew at 90% of light speed, crossing 4 light years. Their calculation placed the dose in a range that would be lethal over the journey duration, without shielding that does not yet exist in any material catalogue. The ship creates its own radiation environment simply by moving. And the radiation problem does not exist in isolation. It interacts with the shielding problem, the heat problem, and the dust problem simultaneously. Each system designed to manage one hazard interferes with the management of another. The crew would need to live inside this for years of ship time. The engineers designing crew quarters would need to solve for radiation exposure, magnetic field exposure, thermal management, and psychological isolation simultaneously, in a vehicle that carries fuel for none of the solutions. What comes after this hits even harder, because the next problem is not about the ship's body. It is about the ship's fuel, or more specifically, a dream about fuel that turned into one of the most elegant failures in the history of propulsion engineering. Every propulsion problem in interstellar travel points toward the same answer when engineers run the numbers far enough. Chemical fuels are not energetic enough. Nuclear fission gives more, but still falls short. Nuclear fusion, if we could sustain it, comes closer. And then the equations point at something that sits at the theoretical peak of energy density for any reaction known to physics. Antimatter. When a particle of matter meets its antimatter counterpart, they annihilate each other completely. Every gram of mass converts entirely into energy. No leftover particles, no waste heat from inefficient combustion, no energy lost to incomplete reaction. The conversion is 100% governed by Einstein's mass-energy equation. Gram for gram antimatter annihilation releases roughly 10 billion times more energy than the best chemical fuel. A ship powered by antimatter annihilation would, in theory, carry far less propellant than any alternative to reach the same speed. The rocket equation finally softens. The mass ratio spiral unwinds. The numbers close in ways they cannot for any other fuel. This is why antimatter propulsion appears in serious interstellar mission studies from organizations including NASA and the European Space Agency. The physics is real, the energy is real, and that is where the good news ends. We cannot make antimatter in meaningful quantities. The largest antimatter production facility on Earth operates at CERN, the particle physics laboratory in Switzerland. Their accelerators produce antiprotons as a byproduct of high-energy collisions at a rate that researchers have measured carefully. The total antimatter produced at CERN across an entire year of operations amounts to roughly 10 nanograms. A nanogram is 1 billionth of a gram. A crewed interstellar mission at even a modest fraction of light speed would require grams of antimatter at minimum, more likely kilograms. The gap between what CERN produces in a year and what a mission requires is 10 orders of magnitude, or roughly 10 billion times more. At current production rates, accumulating enough antimatter for a minimal interstellar mission would take longer than the current age of the universe. The production problem is compounded by the storage problem. Antimatter cannot touch matter. Any container made of matter would cause immediate annihilation. The only proven storage method uses magnetic fields to suspend antiparticles in a vacuum, keeping them from contacting the container walls. These magnetic traps require continuous power. Any interruption, any power loss, causes the antimatter to contact the trap walls and annihilate in an uncontrolled release of energy. The fuel would destroy the ship if the power ever flickered. A crewed mission carrying kilograms of antimatter in magnetic suspension would be carrying an energy release equivalent to multiple nuclear warheads in the cargo hold, held in place by an electrical system that cannot fail once for the entire duration of the journey. Some researchers have proposed harvesting antimatter from natural sources. Cosmic ray collisions produce small quantities naturally, and certain radiation belts around planets contain trapped antiparticles. Harvesting these sources using large collection structures has been studied. The collection rates fall orders of magnitude short of mission requirements. The antimatter dream is the closest physics gets to a genuine solution, and it is still separated from reality by a manufacturing problem that no current technology trajectory solves within any planning horizon. Engineers who accept that antimatter is not available in the needed quantities often turn to a different idea. What if the fuel did not need to be carried at all? What if the ship scooped it up along the way? The concept was brilliant. The physics, examined closely, was cruel. Robert Bussard was a physicist who looked at the interstellar medium and saw a fuel depot stretching across the entire galaxy. In 1960, he published a paper proposing what became known as the Bussard ramjet. The design was striking in its logic. Hydrogen is the most abundant element in the universe. The interstellar medium contains it in dilute but measurable concentrations. A ship with a massive electromagnetic scoop deployed ahead of it could gather hydrogen as it flew, funnel it into a fusion reactor, and burn it for thrust. The fuel source would be the space the ship was traveling through. The faster the ship went, the more hydrogen it scooped per second. The ramjet, in theory, could accelerate indefinitely. Science fiction embraced it immediately. Serious engineers studied it carefully. The problems emerged over the following decade through work by Daniel Whitmire and others, who ran the full physics rather than the conceptual outline. The first problem was the fusion reaction itself. The most common hydrogen isotope in the interstellar medium is protium, ordinary hydrogen with a single proton. Fusing protium is orders of magnitude harder than fusing the heavier isotopes like deuterium and tritium that our best fusion reactors work with. The proton-proton fusion chain that powers stars requires the extreme temperature and pressure found in stellar cores. No engineering concept for a compact shipboard reactor has solved proton-proton fusion at a useful energy output. If you substitute the assumption that fusion somehow works, the second problem arrives: the magnetic scoop. To collect enough hydrogen from the diffuse interstellar medium to feed a fusion reactor capable of meaningful thrust, the scoop field would need to extend across an area hundreds of miles wide. Generating that field requires power. Maintaining it against the pressure of the interstellar gas flowing into it requires power, and the field interacts with the interstellar gas in ways beyond simple collection. Whitmire's analysis, followed by work from other physicists through the 1970s, showed that the drag created by the magnetic scoop interacting with the interstellar medium exceeded the thrust the fusion reactor could produce. The ramjet did not accelerate, it braked. The more powerful the scoop, the more drag it created. The system was self-defeating. A larger scoop to collect more fuel created more resistance than the fuel could overcome. This finding was not immediately accepted. Several researchers proposed modifications, including a laser-augmented version where a forward laser ionizes the incoming hydrogen to make it easier to capture magnetically. The laser requires power. The power comes from the reactor. The reactor needs to be larger to supply both thrust and laser power. the mass ratio grows again. Busard's concept remains elegant as an idea. As a machine, it creates more of the problem than it solves. The galaxy's hydrogen is available in principle and unreachable in practice. There is one more quiet problem that sits behind all of these engineering failures, and it concerns the destination itself. Because even if a ship solved every propulsion, shielding and fuel problem simultaneously, it still faces a target that may have moved, or worse, may no longer exist. The star you are flying toward is real. You can see its light, you can measure its spectrum, calculate its distance, and plot a course. Everything about the navigation feels solid. But the light you are seeing left that star years ago, decades ago, centuries ago, depending on how far away it is. The image of the star in your telescope is a photograph from the past. The star you are looking at is the star as it was, not the star as it is. For nearby targets, the gap is small enough to plan around. Alpha Centauri, the nearest star system, is roughly 4 light-years away. The light arriving in your telescope left 4 years ago. Stellar evolution on a 4-year timescale is negligible. The star is almost certainly still there, still doing roughly what it was doing when the light departed. Go further. A mission targeting a star 60 light-years away receives light that left its source 60 years before launch. The mission travels for decades. By the time the ship arrives, the total elapsed time from the light you planned around could be over a century. For stable, long-lived stars, similar to our own, a century of change is not dramatic. But the universe contains stars that change dramatically on shorter timescales. Variable stars pulse in brightness over days or weeks. Binary systems exchange mass in ways that can destabilize both components. Certain star types are known to produce major flare events that strip away the atmospheres of orbiting planets. The exoplanet in the target system that spectroscopic analysis suggested might be habitable is a measurement of reflected light that is decades old by the time the ship launches. What the planet's atmosphere contained then, what its surface conditions were, is a snapshot. The ship is flying toward the snapshot. For a target with a potentially habitable world, the margin for change over decades is significant. Geological events, atmospheric changes from stellar activity, impacts from passing bodies. None of these are predictable at interstellar distances, and they are all invisible until the ship is close enough to observe directly. There is an additional problem that applies even to the star itself: stellar drift. Stars move through the galaxy. The motion is slow by human standards. But over decades of travel time, the star's actual position shifts measurably from where it appeared to be. A mission planned on a straight-line course toward where the star appears in the sky is aimed at the star's past position. The navigation solution requires calculating where the star will be when the ship arrives, not where it is seen to be when the ship launches. For a mission at low fractions of light speed covering enormous distances, this correction is substantial. The target has moved. The course must account for where it is going, not where it has been. And then there is the rarest, but most absolute scenario. Some stars end, not on human timescales typically, but the universe is old enough that stars in the target range have already died. The star's light reaching Earth shows it alive. The star itself may have already passed through a phase that fundamentally altered the system. A nova, a collapse, a major mass ejection that incinerated any orbiting bodies. The ship is flying toward a postcard. The postcard was accurate when it was printed. What the ship finds when it arrives is unknown until it arrives. And if the destination is gone or altered beyond what the mission planned for, the crew faces that discovery with whatever fuel remains, no resupply, and no timeline for how long they can sustain the mission, in a system that was not what the briefing said. The navigation crisis deepens considerably once you factor in what high velocity does to a crew's ability to orient themselves in real time, which is where the next chapter takes us. A ship at near light speed cannot navigate the way any ship in history has navigated. Every navigation system humanity has ever used, from ancient star charts to satellite positioning networks, relies on a stable, predictable relationship between the observed. You look at a landmark. You measure the angle. You calculate your position. The landmark holds still long enough for the measurement to mean something. At near light speed, nothing holds still. The relativistic aberration described earlier compresses the stars from their true positions into a forward concentrated ring. A navigator looking at the sky sees stars clustered toward the bow, dragged out of their true positions by the ship's velocity. A star that should appear at a specific angle appears somewhere else. The star chart is wrong, not because the chart was drawn incorrectly, but because the ship's velocity has warped the apparent geometry of the universe. To navigate from this distorted view requires real-time correction for aberration, Doppler shift, and the light travel time from each reference star. The calculation is not beyond modern computers, but it requires knowing the ship's exact velocity at every moment to feed into the correction algorithm. Measuring the ship's exact velocity requires observing the stars. The stars are distorted by the velocity. The solution is circular. Engineers have proposed using pulsars as navigation references. Pulsars are rapidly rotating neutron stars that emit beams of radiation with extraordinary regularity, some ticking more precisely than atomic clocks. Their pulse timing is so stable that a receiver tracking several pulsars simultaneously can, in principle, calculate its position in the galaxy to within a few miles. This technique, called pulsar timing navigation, is confirmed physics used in concept development by NASA for deep space missions. At near light speed, pulsar timing still works in principle, but the Doppler shift on the pulsar signals requires continuous correction, and the aberration that displaces the apparent positions of stars equally displaces the apparent positions of pulsars. The correction algorithms become more complex the faster the ship travels. There is a harder limit. At 99% of light speed, the time between pulsar pulses, as measured by the ship's receiver, is compressed by the same factor that compresses everything else. A pulsar that ticks 100 times per second appears to tick hundreds of times per second from the ship's forward-looking receiver. The timing precision that makes pulsars useful gets overwhelmed by relativistic compression. Any course correction at near light speed carries its own engineering crisis. Changing direction requires thrust applied perpendicular to the direction of travel. At low speeds, this is routine. At near light speed, the force required to change course measurably within any reasonable time frame requires an engine firing perpendicular to the main drive. The ship is already carrying barely enough fuel to complete the primary mission. A lateral engine burn of meaningful scale depletes a fuel reserve that the mission cannot afford to lose. The practical conclusion reached by multiple engineering teams studying near-light speed navigation is sobering. The ship must be aimed correctly before it launches. Corrections during flight are possible only within small margins. The mission is committed at the moment the engine lights. If the destination calculation was wrong, or if something changed between launch and arrival, the crew discovers this fact with limited ability to respond. And that is before considering what happens inside the crew themselves over years of this journey, which is the next and arguably most underestimated engineering problem in the entire mission profile. The most efficient way to travel to a distant star is to accelerate continuously at a comfortable rate, cruise at peak speed, then decelerate continuously on approach. Accelerating at a rate equivalent to Earth's surface gravity serves two purposes. It generates thrust, and it simulates gravity for the crew. The human body evolved under gravity. Long-duration weightlessness causes bone density loss, cardiovascular changes, and vision problems from fluid redistribution toward the head. Gravity keeps the crew healthy. The proposal is clean. Accelerate at 1 gravity for the first half of the trip. Flip the ship, decelerate at 1 gravity for the second half. The crew walks normally the entire journey. They sleep in normal beds. Their bodies maintain normal function. The fuel requirement for this mission profile is where the proposal meets the rocket equation again. Continuous 1 gravity acceleration to the midpoint of a trip to a star 4 light-years away, then deceleration, requires an energy output that dwarfs any propulsion system ever built or seriously proposed for near-term development. The mass ratio required under the Tsiolkovsky equation for this mission profile exceeds any physically constructible vehicle. The ship would need to be almost entirely fuel, with the crew compartment representing a fraction of a percent of the total mass. So real mission proposals abandon continuous acceleration. Instead, they propose a boost and coast profile. Accelerate hard for a period, then cut the engines and drift at cruise speed for most of the journey, then decelerate at the far end. The ship reaches its peak speed and then goes quiet. In coast phase, the crew is weightless, and the duration of coast phase for most interstellar distances is measured in years. Medical research from the International Space Station documents what extended weightlessness does. Bone mass decreases at roughly 1% per month. Muscle mass follows. Cardiovascular fitness declines. Vision impairment from intracranial pressure increases has been documented in over half of long-duration astronauts studied. The human body begins dismantling systems it no longer needs in the absence of gravity's constant demand. 6 months is the longest continuous stay aboard the station for most crew members, and return crews require months of physical rehabilitation. A mission with years of weightlessness would produce physical degradation well beyond what the station data currently models. Countermeasures exist: resistance exercise, fluid management protocols, medications. Their effectiveness at preventing the full scope of long-duration changes is unproven at the timescales interstellar missions require. A crew arriving at their destination after years of coast phase may be physically compromised at the moment they most need full capability. Some proposals address this with a rotating habitat. Spin a section of the ship fast enough, and centrifugal force simulates gravity in that section. This works in physics. In engineering, it introduces new complications: rotating seals that must not fail, gyroscopic effects on the ship's attitude control, vibration management. Achievable, most engineers agree, but at a cost in mass and complexity that the rocket equation registers immediately. The human body was not engineered for this mission. It was optimized for a planet with a specific gravity, specific atmospheric composition, specific light cycle, and specific social density. None of those conditions exist on the ship, and the psychological consequences of that mismatch over years of isolation are, by some measures, the problem most likely to end the mission before the physics does. NASA has spent decades studying isolated, confined environments, Antarctic research stations, submarine deployments, the International Space Station. Every dataset they have collected points to the same conclusion: humans in small groups, cut off from the outside world, confined together for extended periods, develop predictable psychological problems. The third quarter phenomenon appears in almost every long-duration isolated mission studied. Crew performance, mood stability, and interpersonal relations all degrade in the period roughly 3/4 of the way through a mission. Teams that functioned well in the first half begin showing friction, disengagement, and what researchers call behavioral drift in the third quarter. The pattern holds across environments and crew compositions. For a 6-month station deployment, the third quarter effect is manageable. Crew rotations, communication with Earth, resupply missions, and the psychological support of knowing the mission has a fixed end date all provide stabilizing anchors. A near-light-speed interstellar mission removes every one of those anchors simultaneously. Communication with Earth degrades from real-time to delayed to essentially one-way as the ship accelerates. Resupply is physically impossible. The crew carries everything they will ever have, and the end date is not a return to Earth, but an arrival at a destination that has never been visited, whose conditions are uncertain, and where the crew is entirely on their own. Researchers at institutions including the University of Hawaii and the Mars Desert Research Station have modeled the psychological requirements for long-duration isolated missions and consistently identify the same critical factors: crew selection, conflict resolution structure, and meaningful work throughout the journey. Crew selection for an interstellar mission is a selection problem with no historical precedent. The individuals chosen would need to function together for years under conditions of absolute confinement, total communication isolation, and the knowledge that everyone they knew on Earth is aging rapidly or already gone due to time dilation. They would need to manage conflict without external mediation, maintain motivation without external validation, and sustain performance without the social context that humans depend on for psychological health. Mission planners have proposed various structures: hierarchical command systems that clearly define authority, rotating leadership to prevent stagnation, mandatory structured downtime, scheduled communication windows, even when the content of those communications is meaningless due to signal delay. One element no proposal has cleanly solved is grief. The crew members of an interstellar mission would know from the moment of launch that the world they knew is changing beyond their reach. Every month of ship time is months or years of Earth time lost. Parents age, children grow, partners live entire chapters of life that the crew member will never share. This grief begins at launch and compounds continuously. Psychologists who study this dynamic have noted that it resembles anticipatory grief in terminal illness, where the loss is known in advance and must be processed while the person continues to function. The difference is that interstellar crew members must sustain high-performance technical work while managing that grief in isolation with the same small group of people indefinitely. No psychological screening tool currently identifies individuals who can do this with certainty. The population of humans capable of it may be very small. Whether it is large enough to staff an interstellar mission crew is a question the research does not yet answer. What the research does consistently suggest is that the mission itself must feel meaningful enough to sustain the crew through everything the psychology is working against. And the dimension of meaning that matters most is not personal, it is civilizational. The moment a civilization commits to a near light speed mission, it makes a statement about itself that goes beyond the engineering. Every other space mission humanity has launched has been in some form recoverable. Missions fail, astronauts have died, but the institutional knowledge returns. The crew of Apollo 13 came home. The lessons of the Challenger disaster fed back into the program. Even unmanned missions that failed produced data about why they failed, data that improved the next attempt. A near-light speed interstellar mission is severed from that feedback loop at launch. The crew departs. Due to time dilation, the mission planners who design the systems they are using age and retire and die while the ship is still in transit. The engineers who could diagnose a specific failure mode are gone before the mission arrives. If something goes wrong that the crew cannot solve with the resources on the ship, there is no external knowledge base to draw on. Earth cannot help in any practical sense by the time it receives a distress signal and formulates a response. The civilization that launches the mission is not the civilization the crew returns to, if they return at all. Politically, scientifically, culturally, the world moves. Funding priorities change. The agency that ran the mission may no longer exist in the same form. The mission itself may have been forgotten, then rediscovered, then forgotten again in the decades of Earth time that passed during transit. Historians who study long-term institutional continuity point to a hard limit. Most human institutions do not sustain a singular focus across more than 3 or 4 generations without fundamental restructuring. A mission requiring support across a century of Earth time is asking an institution to hold a priority longer than most institutions in history have held anything. There is also the question of what the mission means for the civilization's self-understanding. Every culture that has ever existed has defined itself partly by geography, by the boundary between home and not home. A mission that sends crew members to a destination with no return collapses that boundary in a way that no previous exploration has done. The explorers who crossed oceans returned with stories, goods, and knowledge that fed back into the societies that sent them. The interstellar crew, if they send anything back, send it at the speed of light across years of distance. What arrives on Earth is not a person with a story. It is a data signal, degraded by distance, carrying information that Earth scientists may spend years interpreting. The psychological and civilizational weight of this is something that engineers do not often calculate, but it sits behind every serious interstellar proposal. The decision to launch is permanent in a way no other mission decision has ever been. The ship does not carry a crew on an expedition. It carries a civilization's investment into a one-way conversation with the cosmos, and the physical laws waiting at the absolute edge of this conversation, the boundary where light speed becomes a true wall, rather than an engineering challenge, are where this mission profile finally meets its hardest limit of all. That limit has a name, and what it means for any signal, any ship, any hope of meaningful return across it, is coming next. Draw a point on a piece of paper. That point is you, right now, in this moment. Draw a cone spreading upward from it, widening as it rises. Everything inside that cone is every place you could possibly reach moving forward in time, at any speed up to light speed. Physicists call it the future light cone. Everything outside the cone is unreachable. Forever, The geometry is absolute. No engine, no shortcut, no clever routing changes this. The cone's boundary is the speed of light, and the boundary holds everywhere in the universe equally. Now put the ship at launch. The moment the engines ignite, the ship's light cone begins moving away from Earth's light cone, slowly at first. As the ship accelerates, the two cones separate. Events that fall inside Earth's future but outside the ship's future cone become invisible to the crew. Events that fall inside the ship's future but outside Earth's light cone become invisible to mission control. At near light speed, this separation becomes operationally significant. There are things happening on Earth that the crew will never know about, not because communication is slow, but because the geometry of space-time places those events outside the region the crew's light cone can ever reach. The separation is not a technical problem. It is a structural feature of how the universe is organized. At true light speed, the situation becomes absolute. A ship traveling at exactly light speed, if such a thing were possible, would have a future light cone that runs perfectly parallel to its direction of travel. The cone never intersects with Earth's light cone again. No signal from Earth ever catches the ship. No signal from the ship ever indicates where it went after the moment it hit light speed. The ship vanishes from Earth's causal universe entirely. This is the light cone boundary. It is not a barrier you crash into. It is a geometric fact about the structure of space-time that means once the ship crosses that threshold, the conversation between crew and Earth ends permanently. From Earth's perspective, the ship's last known position and the last signal received are the entirety of the mission record. Everything after is silence. From the crew's perspective, something even stranger happens. At light speed, photons from behind the ship can never catch up. The crew loses the ability to receive any new information from Earth. The universe behind them goes dark. Every star, every galaxy behind the ship freezes into the last image received at the moment they hit the speed threshold. They are flying blind into a future that Earth cannot share and cannot witness. The light cone boundary is why physicists say light speed travel is not just an engineering challenge. It is a civilizational severing. The ship does not go on a mission. The ship leaves. And what it leaves behind is a civilization that sent something irreplaceable into a region of space-time it can never access again. The information the crew gathers, the discoveries they make, the fate they experience, all of it exists in a bubble the universe has sealed off from Earth's causal reach. Some theorists have proposed using quantum entanglement to maintain communication across this boundary. Entanglement links particles in ways that seem to transcend distance. The problem is confirmed by decades of experiment. Entanglement cannot transmit information. The correlation between entangled particles is real, but it cannot be used to send a signal. The light cone boundary holds even in quantum mechanics. There is one concept that appears, on the surface, to break this rule. It involves not moving through space faster than light, but moving space itself. It is the most discussed and most misunderstood proposal in interstellar travel. And its energy requirement makes everything discussed so far look modest by comparison. In 1994, a physicist named Miguel Alcubierre published a paper that spread through the scientific community at a speed that felt almost appropriate to its subject. He had found a solution within Einstein's own equations of general relativity that described a bubble of flat spacetime moving through curved space. Inside the bubble, the laws of physics operate normally. The crew experiences no acceleration, no time dilation, no relativistic headwind. Outside the bubble, the space ahead contracts and the space behind expands. The bubble, and everything inside it, moves across the universe faster than light. The ship is not moving through space faster than light. The space itself is moving, carrying the ship along. Alcubierre's solution technically obeys relativity, because it exploits the fact that space-time itself has no speed limit. Space expanded faster than light in the moments after the universe began. His drive was, in concept, a controlled version of that same expansion. The physics community examined it carefully. The math was valid. The geometry worked within the framework of general relativity. For a brief period, it appeared that someone had found a genuine loophole. Then the energy calculation arrived. To generate the space-time distortion described by Alcubierre's geometry, the drive requires a region of negative energy density. Positive energy, which is everything humans have ever observed or worked with, curves space-time one way. Negative energy curves it the other way. The bubble requires a specific configuration of negative energy wrapped around it to maintain the geometry. Negative energy is real. The Casimir effect, confirmed experimentally, demonstrates that the vacuum of space between two closely spaced metal plates contains less energy than the vacuum outside, a measurable negative energy density. The effect is tiny and localized, but it exists. The problem is quantity. Alcubierre's original paper did not calculate how much exotic negative energy the drive required. When physicist Harold White at NASA recalculated the requirements with more optimistic geometry assumptions in 2012, his result was still a quantity of exotic matter with a mass-energy equivalent comparable to a large planet. Later analyses with different geometric constraints produced different numbers, some larger, some smaller, but all far beyond anything that exists or could be produced. The total negative energy in the observable universe may not be sufficient to power one Alcubierre drive at the scales proposed. There is a second problem that the geometry creates. Inside the bubble, causality is preserved. The crew experiences normal physics. Outside the bubble, the space-time distortion creates closed, time-like curves, paths through space-time that loop back on themselves. Physicists call these time loops. A ship using an Alcubierre drive might, in principle, arrive before it departed. This violates causality in ways that most physicists believe the universe prevents through mechanisms not yet fully understood. Stephen Hawking proposed what he called the chronology protection conjecture. The universe appears to prevent the formation of time machines through quantum effects that destroy the geometry before it fully forms. The conjecture is not proven. It is supported by strong theoretical arguments, but has not been experimentally tested at the scales required. So, the Alcubierre drive sits in an unusual category. It is mathematically valid within general relativity. It requires a form of energy that exists in principle but not in any useful quantity. And it may produce causality violations that the universe itself prevents. 3 separate barriers, each individually decisive, stacked behind a proposal that cannot be tested because reaching the first barrier requires capabilities centuries beyond our current state. The drive cannot be built, the energy cannot be made, and even if both problems were solved, the universe may refuse to cooperate. The wormhole, proposed decades earlier, offers a different geometry, different physics, and a return path that looks, on paper, more achievable. But the energy problem waiting inside it is nearly identical, and the structural instability that kills every wormhole proposal makes the Alcubierre barriers look manageable by comparison. The concept of a wormhole comes directly from Einstein's equations, developed alongside physicist Nathan Rosen in 1935. They described a theoretical bridge connecting 2 separate regions of spacetime, a tunnel through the universe's geometry rather than a path across it. Travel through the tunnel and you emerge somewhere else, potentially somewhere very far away, without having crossed the intervening distance. For interstellar travel, and specifically for the return problem, wormholes are the theoretical solution that keeps appearing in serious discussions. A ship enters the wormhole near Earth, exits near the destination star, completes the mission, and returns through the same tunnel. No one-way ticket. No time dilation accumulation from a decades-long journey. No fuel crisis from crossing light years under propulsion. The concept is scientifically legitimate. General relativity permits wormhole solutions. The equations do not forbid them. Whether the universe actually creates them, or whether they can be created artificially, is a separate question, and the answer from current evidence is discouraging. Natural wormholes, if they exist at all, would form at the Planck scale, the smallest meaningful size in physics, at roughly 1/10 trillionth of a trillionth of a centimeter across. A structure this size cannot pass anything, including light. To be useful for travel, it would need to be expanded by an enormous factor, and the mechanism for that expansion requires exotic matter with negative energy density, the same ingredient the Alcubierre drive demands. The stability problem is more immediate. A wormhole held open by normal matter collapses. The geometry is inherently unstable under positive energy. The moment you try to send anything through it, the throat of the wormhole pinches off. The transit time through the wormhole may be shorter than the time it takes for the structure to collapse around whatever is passing through it. To stabilize the throat requires threading it with negative energy matter, exotic material with properties no naturally occurring substance possesses. The quantity required scales with the size of the wormhole. For a throat wide enough to pass a crewed ship, the exotic matter requirement reaches a scale that competes with the Alcubierre drive's demand. Physicist Kip Thorne, who developed the traversable wormhole concept, with colleagues in the 1980s, as a thought experiment for Carl Sagan's novel Contact, was explicit about the exotic matter requirement in his own follow-up research. The traversable wormhole is not forbidden by physics. It is forbidden by the unavailability of the materials it requires. There is an additional constraint that does not appear in most popular discussions. Even a stable, traversable wormhole does not automatically provide a shortcut to a specific destination. The far end of the wormhole opens somewhere, directing where it opens, threading one end to a specific star system light years away, requires a level of control over space-time geometry that goes beyond simply building the wormhole. The engineering of placement has no worked solution. Some theorists have proposed finding naturally occurring wormholes and then engineering their endpoints to desired locations. Finding them requires detecting space-time distortions at scales and locations we have no telescope positioned to survey. Redirecting a natural wormhole's endpoint requires exerting force on a space-time structure using mechanisms that do not exist. The wormhole solves the return problem on paper. On paper is where it stays. Physicists who work on these solutions are not discouraged by this, because the value of the work is theoretical. Understanding the conditions under which these geometries could exist tells us things about the universe's structure that no telescope can reveal. But mission planners looking for a return path cannot plan around a solution that requires materials the universe may not contain in usable form. What remains when all the exotic solutions are set aside is a harder question. If return is impossible through physics and engineering alike, what does a serious mission actually look like? The answer that appears in real planning documents is colder than any equation. Read the mission documents carefully, not the press releases. Not the summaries written for public audiences. The actual technical documents, the ones produced by physicists and aerospace engineers working under real budget constraints, with real physics constraining every line. They all arrive at the same admission, placed in different sections, worded in different ways, but carrying the same weight. The mission is one way. Breakthrough Starshot's documentation describes a flyby mission with no deceleration stage. The design team's own papers acknowledge that a crude version scaling from the same principles would face return fuel requirements beyond current and projected near-term engineering capacity. Their solution was to remove the return from the mission profile entirely and reframe the science goal as data transmission during a flyby window. Project Icarus, a formal study by the British Interplanetary Society that ran from 2009 to 2013, spent 4 years and contributions from dozens of engineers developing a fusion-powered interstellar probe. Their target was a flyby of a nearby star system within 100 years of travel time. Crewed mission variants were discussed. The deceleration mass budget in every crewed variant consumed fuel reserves the design could not carry. Icarus concluded that a crewed version required technologies classified as speculative, even within an optimistic development timeline. The Tau Zero Foundation, a group of researchers dedicated specifically to practical interstellar travel studies, has published assessments of what technologies would be required for a genuine crewed round-trip mission. Their minimum requirements include fusion propulsion at efficiencies beyond current experimental results, deceleration systems requiring either magnetic braking structures of unprecedented scale or antimatter reserves in quantities discussed in earlier chapters, and life support systems sustaining a crew through a multi-decade journey with no resupply. Every item on the list is described as requiring fundamental breakthroughs, not incremental improvements. A fundamental breakthrough is not a version of something we already have. It is a new category of capability that does not yet exist in any laboratory. The pattern across these studies is consistent. Engineers who engage honestly with the physics of interstellar travel at near light speed find the same barriers every time, approached from different directions using different optimistic adjustments applied. The barriers hold. What is notable is that these studies continue, not because the engineers believe the barriers will fall tomorrow, but because the exercise of finding where they hold produces knowledge useful for the next generation of spacecraft, for the probes flying in the solar system today, for the propulsion research that might eventually close some of the gaps. There is also something specific that these engineering teams have learned about themselves in the process. When you spend years working on a mission that physics constrains to one way, and you work on it seriously and honestly, something happens to your perspective on the mission's purpose. The question stops being how do we return, and starts being what justifies going. That reframe produces a different kind of mission design, and the concept that emerges from it has a name. It is older than the rocket equation. It is the only interstellar mission profile that does not immediately break against the fuel math. And it faces almost every problem discussed so far, just on a longer timeline. The generation ship concept accepts what near-light speed proposals fight against. It says, we cannot go fast enough to make the trip feel short, so we build the ship large enough to make the trip last forever, comfortably, across multiple human generations, until descendants of the original crew arrive at the destination. A generation ship does not need exotic propulsion. It does not need to solve the rocket equation at light speed fractions. It can travel at a fraction of 1% of light speed, propelled by nuclear or fusion drives that are at least theoretically constructible from existing physics. It trades time for tractability. The design requirements shift from propulsion physics to ecology and sociology. The ship needs to function as a closed biosphere for potentially hundreds of years. Food, water, air, waste, all of it must cycle internally with zero net loss because there is no resupply. The crew grows, ages, and dies aboard. Their children are born citizens of the ship, raised for a world they will never personally reach. Their grandchildren will be the first to see the destination star grow from a point of light into a disk. The engineering of a closed ecological system at the scale required for multi-generational habitation is a real and unresolved problem. Biosphere 2, an experimental closed environment built in Arizona in the late 1980s, housed 8 people in a sealed structure. For 2 years, oxygen levels dropped dangerously. Populations of pollinating insects collapsed. Food production fell short of planned yields. The experiment survived, but revealed how far human engineering is from sustaining a closed system reliably over the long durations a generation ship requires. Scale the problem to a ship population large enough to maintain genetic diversity across hundreds of years, and geneticists estimate a minimum viable founding population, somewhere between 100 and several hundred individuals, possibly more. The ship must sustain that population's genetics, healthcare, education, and social structure across time spans longer than most human civilizations have remained coherent. The sociological problem is potentially harder than the biological one. The original crew chose this mission. They understood what they were committing to, or could be selected for the psychological profile that makes that commitment stable. Their children did not choose it. The generation born on the ship inherits a mission they had no voice in accepting. Philosophers and mission theorists have debated whether this constitutes an ethical violation. No consensus exists. There is also the institutional problem raised in a previous chapter. Now amplified across centuries, the mission requires that the ship's governing structure, its social norms, its maintenance culture, and its mission focus all survive intact through generations of humans who have no direct experience of Earth, no external input from Earth due to light travel time, and no ability to course correct from outside their own closed system. Institutions that form in isolation, cut off from external accountability, have a documented historical tendency toward drift, toward the optimization of the institution's internal logic over its original external purpose. And then there is the return problem, unchanged from every other mission profile. The generation ship that arrives at its destination faces the same empty fuel tank, the same hostile interstellar medium, the same deceleration problem. It arrives and decelerates at the cost of fuel that represents the entire propulsion budget for a return. The descendants who step out into the new system do not have a ship capable of coming home. The generation ship solves the travel time problem. Every other problem follows it through the door. The most unglamorous problem in near light speed travel does not involve exotic matter or quantum mechanics. It involves heat, specifically the inability to get rid of it. Every energy conversion process generates waste heat. Every engine, every computer, every light source, every human body produces thermal energy as a byproduct of operation. In a terrestrial environment, that heat dissipates into the surrounding air, into the ground, into flowing water. In space, none of those mechanisms exist. The only way to shed heat in a vacuum is through thermal radiation, the emission of infrared light from warm surfaces. For spacecraft operating in the inner solar system, thermal management is a known and solvable problem. Radiator panels extend from the International Space Station, releasing heat into space as infrared radiation. The station's thermal control system is one of its most critical subsystems. Engineers have spent decades optimizing it. A near-light speed ship makes the problem radically worse in ways that are not immediately obvious. First, the sheer energy throughput of any propulsion system capable of reaching meaningful fractions of light speed produces waste heat at rates that exceed anything current radiator technology can manage. Even a fusion drive operating at high efficiency produces enormous waste heat from plasma exhaust, magnetic confinement systems, and energy conversion losses. The radiator area required to shed that heat scales directly with the power level. At propulsion power levels required for near-light speed acceleration, the radiator surface area required is estimated in serious engineering analyses to be on the order of many square miles. A ship with square miles of radiating surface is structurally enormous. Structural mass goes into the rocket equation immediately, demanding more fuel to accelerate all that extra mass, which produces more heat, which requires more radiator area. Second, the relativistic headwind described earlier bombards the forward surfaces of the ship with concentrated radiation. That energy is absorbed by the hull and converted to heat. The same surface that needs to radiate waste heat from internal systems is simultaneously absorbing radiation from the relativistic environment outside. The net thermal load on the hull increases steeply with velocity. Third, the interstellar medium itself deposits energy into the hull through particle impacts. Each dust grain and gas molecule that strikes the hull at near light speed contributes kinetic energy that the hull absorbs as heat. At the impact rates calculated for near light speed travel, this represents a continuous energy input that the thermal management system must also handle. Materials science offers limited help. The best thermal radiators known are carbon-based structures that operate at high temperatures and emit efficiently. At the thermal loads projected for near-light speed missions, these materials approach their operational limits quickly. New materials with dramatically better thermal properties have not emerged from any research program currently active. The thermal problem does not have a clever workaround. It is a fundamental consequence of operating at high energy levels in an environment where heat can only leave the ship one way. Every second of high thrust operation pushes the ship's thermal management system closer to its limits. Some engineering proposals have suggested operating the drive in pulses, allowing radiators to shed heat between burns. At the power levels and pulse durations required to accelerate a crewed ship to near light speed fractions, the intervals required between pulses extend the total mission duration dramatically. The mission that should take years of acceleration stretches into decades of pulsed operation. The thermal crisis is quiet, unglamorous, and absolute, and it operates in parallel with every other problem on this list, simultaneously. What comes next operates at a scale even smaller than a heat particle, at the level of the quantum vacuum itself, and the implications are stranger than the thermal math suggests. Quantum mechanics describes a universe that is never truly at rest, even in a perfect vacuum, completely empty of matter and radiation. The laws of quantum physics permit pairs of particles to spontaneously appear, one matter, one antimatter, existing for a fraction of a second before annihilating each other and returning their energy to the vacuum. These are called virtual particles, and they are not theoretical constructs. Their effects are measurable. The Casimir effect, the Lamb shift in hydrogen spectral lines, the anomalous magnetic moment of the electron. All of these confirmed experimental results arise directly from virtual particle effects in the quantum vacuum. The vacuum is not empty. It seethes. For a ship sitting still or moving slowly, the virtual particle activity of the vacuum is symmetric. Particles appear and vanish in all directions equally. The net effect on the ship is negligible. A ship moving at near light speed breaks that symmetry. The effect is called Unruh radiation, predicted by physicist William Unruh in 1976, and confirmed through theoretical cross-checks with related quantum field theory phenomena. An accelerating observer in a vacuum does not experience the same vacuum as a stationary observer. The acceleration converts the virtual particle activity of the vacuum into real detectable thermal radiation from the observer's perspective. The faster the acceleration, the higher the temperature of the Unruh radiation the observer experiences. For everyday accelerations, the Unruh temperature is so small it is unmeasurable with current instruments. At the accelerations required to reach meaningful fractions of light speed within reasonable timeframes, the Unruh temperature rises into ranges that have practical consequences for sensitive instruments, and at extreme accelerations into ranges relevant to crew health. A ship accelerating at rates required to reach 90% of light speed within a year, rather than over a decade of gentle acceleration, would experience Unruh radiation temperatures measurable and potentially relevant to electronics and biological tissue. The effect is not the mission-ending crisis that the dust grain problem or the fuel math represents. It is one more thermal and radiation load added to the cumulative stress the ship experiences, one more input the thermal management system must handle, one more source of radiation the crew's shielding must account for. What makes it significant is its source. The radiation does not come from outside the ship, from stars, or the interstellar medium. It comes from the vacuum itself, generated by the ship's own acceleration. The ship's movement creates its own hostile environment from the fabric of space-time. The faster it accelerates, the more radiation it generates from nothing. There is a related phenomenon that applies even to constant velocity at near light speed, not just acceleration. At high enough velocities, the cosmic microwave background radiation, normally a diffuse bath of cold microwave photons, filling the universe uniformly, blue shifts from the forward direction into increasingly energetic radiation. At near light speed, this background radiation becomes a significant radiation source from the ship's forward hemisphere. The universe's own background warmth becomes a directed beam aimed at anyone moving fast enough through it. Every layer of this problem that gets examined reveals another layer beneath it. The ship is not moving through a passive medium. It is moving through a quantum fabric that responds to its presence, its velocity, and its acceleration, with effects that compound across every other system. And all of this has been building toward one number, one specific threshold, where the physics stops being a collection of engineering challenges and becomes something more final than any of them separately. Every mission has a turnaround point, a moment in the journey where enough fuel remains to reverse course and return home. Past that point, the mission is committed. The crew continues forward. For near light speed missions, that turnaround point arrives far earlier than intuition suggests. The calculation is straightforward in concept. The ship carries a total fuel load at launch. As it accelerates, fuel burns. The remaining fuel at any given moment determines the maximum velocity change the ship can still perform. A return trip requires enough velocity change to stop the outbound motion and then accelerate back toward Earth. That is a very large velocity change, roughly twice the mission's peak speed, applied after the ship has already burned through a significant fraction of its fuel. Run the numbers for a mission targeting a nearby star at 50% of light speed with realistic fuel efficiency. The turnaround point where sufficient fuel remains for a return falls within the first few percent of the total distance. A mission traveling 4 light years turns around, if it turns around at all, within the first fraction of a light year. Past that threshold, the physics of return close like a door. This is why engineers describe the point of no return as an early feature of the mission profile rather than a late one. The window where return is possible is narrow and comes before the ship has traveled far enough to gather any scientifically meaningful data about the destination. A ship that could return home has not gone far enough to justify the mission. A ship that has gone far enough cannot return. The point of no return is baked into the mathematics before the first bolt is tightened. Some proposals have tried to engineer around this by staging the mission. A larger carrier ship accelerates a smaller inner vessel, drops it off at near light speed, then decelerates and waits at a midpoint, while the inner vessel completes the mission. The inner vessel returns at near light speed to the waiting carrier, which then burns home. The approach distributes the fuel budget across two separate vehicles and two separate phases. The mass ratio problem applies to both vehicles separately. The carrier must be large enough to decelerate itself, wait, and return. The inner vessel must be self-sufficient for the mission duration. The total launch mass, adding both vehicles and their fuel requirements, grows past the point where any single launch infrastructure we have built could deliver it to orbit. Stage return concepts exist in the engineering literature. They have not been dismissed as impossible in the way that some proposals have. They are classified as requiring technologies several generations beyond current capability, including propulsion systems, fuel types, and materials that do not yet exist experimentally. The point of no return is also a psychological threshold that mission planners discuss in terms of crew commitment. Every long-duration mission has a moment where the crew fully internalizes that they are past the option to change their minds. Astronauts and researchers who have experienced this in Antarctic winter over deployment describe it as a genuine shift in mental state. The option closing sharpens focus for some crew members and destabilizes others. For an interstellar mission, that threshold arrives not at some dramatic physical landmark, but at a number logged quietly in the fuel management system. One day, the remaining propellant drops below the minimum required for return. No alarm sounds. The ship continues flying. The crew may not be told immediately. The mission documentation of several serious studies discusses how and when to communicate the point of no return to crew, and whether doing so serves the mission or damages crew psychology. The only interstellar mission concept that avoids this conversation entirely is the one that never planned for return in the first place. And that concept, the permanent transfer rather than the expedition, raises the hardest question about what kind of civilization chooses to send it. Strip away every constraint that makes the physics hard. Give the mission unlimited fuel. Solve the deceleration problem. Shield the crew perfectly. Ignore the psychological burden. Make the navigation exact. Run every system at theoretical maximum efficiency. One problem remains. Even in this idealized scenario, a ship returning from a near-light speed interstellar mission returns to a future Earth. The time dilation accumulated during the round trip is permanent and real. A mission crew that experiences 10 years of ship time while Earth ages 70 years cannot recover those 60 years. They return to an Earth 60 years ahead of the one they left. That gap is not a malfunction. It is a confirmed physical consequence of the journey. Return, in the strict sense of returning to the world you left, is impossible at any fraction of light speed that makes interstellar travel feasible. You can return to Earth. You cannot return to your moment. The one theoretical scenario where something closer to genuine return exists requires a configuration that no single civilization can build alone. Imagine two identical ships. Ship A launches from Earth toward a target star system. Ship B is somehow already at that destination, launched by another civilization or placed there by a prior unmanned mission, carrying the necessary technology. When Ship A arrives after its near-light speed journey, it uses Ship B's fuel and propulsion to decelerate and return. Ship B was waiting with everything Ship A burned through on arrival. The math on this closes. A returning ship that does not carry its own deceleration fuel, because a waiting vessel provides it, can make the round trip within the bounds of physics. The crew still experiences time dilation on the return leg. They still arrive home to a future Earth. But the mission at least physically completes the round trip. The requirement for this scenario to work is a second ship at the destination before the first ship arrives. Placing that ship there requires either a prior near-light speed mission that itself had no return, a very long-duration slower mission launched far earlier, or a civilization already at the destination willing to provide the fuel. The first option requires you to have already solved the one-way mission problem before the two-way mission. The second option requires launching a generation ship or similarly slow vessel decades or centuries before the crewed near-light-speed mission, meaning the slow ship must have arrived and remained operational, and its fuel must still be available when the fast ship arrives. The third option requires contact with another technological civilization capable of spaceflight. Every branch of this solution requires solving a problem equivalent in difficulty to the original mission. The scenario is theoretically coherent. It is practically closed to any near-term planning horizon. Researchers who have outlined it in the literature describe it as a second-generation mission concept, something that becomes possible only after prior missions have established infrastructure at the destination, which itself requires prior missions to have succeeded. The return problem does not have a solution available to a first mission. The first mission goes one way. If there is ever a second mission, it finds what the first one left behind. This is the template the universe appears to have written for interstellar travel. The first ones through the door do not come back. What comes through the door in the other direction, much later, is whatever they managed to build after they arrived. The Fermi paradox asks a question that has never been adequately answered. The universe is roughly 14 billion years old. Stars similar to our own formed billions of years before ours did. Any civilization that arose around those older stars had billions of years more than we have had to develop technology, expand into space, and make their presence felt across the galaxy. Where are they? The physics of near-light speed travel and the one-way nature of any ship that approaches that threshold may be part of the answer. A civilization that develops genuine interstellar propulsion, even at modest fractions of light speed, faces the same physics we face. Their ships accelerate, their fuel burns, their point of no return arrives early in the mission profile. Their crews, if they send crews, leave and do not return in any meaningful civilizational sense. A civilization advanced enough to send ships to neighboring star systems is also advanced enough to understand precisely what those ships are committing to. They know the time dilation numbers. They know the communication blackout timeline. They know that the crews who depart are departing into a causal bubble that will never fully intersect with the home civilization again. What does a civilization do with that knowledge? Several scenarios follow from it. The civilization may choose to send only automated probes, which removes the ethical burden of sending beings who cannot return, but also removes any crew capable of making on-site decisions. The probes arrive, transmit data home across the light-year gap, and continue. Earth, right now, is effectively doing this. We have sent probes. None carry crews. None return. A civilization may develop the capacity for near-light speed travel and then choose not to use it for crewed missions, because the one-way nature makes it a civilizational sacrifice rather than an exploration program. The political will to commit permanent crew losses may simply not exist in stable, long-lived civilizations. A third possibility follows from the time dilation math. A civilization that sends a crew to a nearby star receives back a transmission some years later. Time dilation means the crew aged less than Earth did during the journey. If the crew transmits knowledge gained at the destination, that knowledge arrives at Earth from people who are biologically younger than their peers who stayed home. The civilization that sent the mission is ahead of where it would have been without it in terms of information. But the crew that generated that information has been severed from home in every practical sense. Over many such missions, launched at intervals, a civilization might gradually extend its knowledge of neighboring systems while never successfully establishing a two-way relationship with any of them. Each mission is an investment with a one-directional return. Information flows back, crew does not. Whether an advanced civilization finds this acceptable depends on values we cannot predict. Whether any civilization has done it, somewhere in the galaxy's history, and what the receiving end of that one-directional information flow eventually built, is a question the galaxy holds silently. The silence of the cosmos may not be a sign that no one is out there. It may be a sign that everyone who tried to cross the distance learned what we are learning now, and made the same choice we will eventually have to make. Voyager 1 has been traveling for nearly 50 years. It is now beyond the heliopause, the boundary where our star's solar wind yields to the interstellar medium. It is, technically, in interstellar space. It travels at roughly 38,000 miles per hour. At that speed, it would take over 70,000 years to reach the nearest star system. It will never get there. Its power source will fail within the next decade. It will then drift silently through the galaxy as a metal artifact of a civilization that will not be identifiable from its surface by the time it passes anything interesting. Voyager 1 is a one-way mission. So is Voyager 2. So are Pioneer 10 and Pioneer 11. New Horizons, which flew through the Pluto system and is now headed into the outer solar system, is a one-way mission. Every probe humanity has ever launched beyond Earth orbit has been a one-way mission. We have been sending one-way tickets into space since the 1970s. We called them science missions. We designed them to transmit data home. We never built them to return because the fuel and engineering required for return was always beyond the mission budget. We made a practical decision, project by project, and the cumulative result is a fleet of one-way ambassadors now scattered through space, with no ability to come home. The pattern is the template. When the first crewed interstellar mission launches, if it ever does, it will represent a scaling of the same decision, already made dozens of times for unmanned probes. The mission goes, data comes back. The hardware does not return. The difference is that this time, the hardware is people. That difference is enormous in ethical terms, and essentially zero in engineering terms. The physics does not distinguish between a camera and a crew member. The rocket equation applies equally. The one-way nature of the mission follows from the same constraints. What the probe era tells us is that humanity already accepts one-way missions, when the scientific return justifies the cost, and when the thing being sent is not a person. The question the probe era has been silently preparing us for is when and whether we will accept the same trade when the payload is human. The space agencies that plan long-term have documents that address this. They exist in the speculative planning literature of NASA, the European Space Agency, and others. They discuss crewed interstellar missions in timescales measured in centuries, contingent on propulsion breakthroughs, contingent on a dozen categories of technology that do not yet exist. The documents are honest. They frame the crewed interstellar mission as a goal requiring multiple generations of technological development. They do not promise a return. They describe a mission that goes. Every probe we have launched has been practiced for that decision. The engineering lessons from each one feed into the next. The thermal management of New Horizons, the power systems of the Voyagers, the navigation precision of the missions beyond the solar system. All of it accumulates toward a design language for ships that travel one way into the deep dark and transmit what they find. The next decision is whether to put a crew inside one, and that decision lives at an intersection of engineering, ethics, and civilizational purpose that the math alone cannot resolve. What can be said with certainty is that the physics has already decided one thing. The ship that goes does not come back. And the last chapter of this mission, the one nobody writes into the planning documents, is what happens to the civilization that watches the signal fade. The ship accelerates. Somewhere in the outer solar system, a receiving array the size of a city block tracks the narrowing beam of the ship's transmitter. The signal is already redshifting. Engineers on duty adjust the receiver frequency in small increments, chasing the Doppler curve they calculated years ago in pre-flight planning. The crew's voice arrives with a slight pitch drop, a subtle stretching that the software corrects before anyone on the operations floor hears it. For now, everything sounds normal. The words are intelligible. The emotional content is present. Someone in the crew compartment made a joke about the coffee. Mission Control laughed 8 hours after it was said. Over the following months, the delay extends. The voice quality degrades. The software corrections become more aggressive, pulling signal from increasing noise. The data rate drops. What was once a continuous audio and video stream becomes a compressed packet transmission, then a data-only stream, then a periodic telemetry burst. The crew's messages get shorter, not because they have less to say, but because the bandwidth to send it has shrunk to a trickle. Mission Control's replies take longer to arrive on the ship than the crew's shift cycles. The conversation becomes geological. A question asked today receives an answer that arrives after the crew member who asked it has gone through several sleep cycles, changed assignment, or resolved the issue independently. At some point, the message from Mission Control reads, "We received your transmission from 14 months ago. You reported a minor coolant anomaly in the secondary loop. We have reviewed the telemetry and believe the issue resolved without intervention. Please confirm current status. The crew's response, confirming that yes, it resolved, that this was 14 months ago, and everyone aboard has long since moved on, arrives at mission control 2 years after the original anomaly occurred. The connection does not break suddenly. It attenuates. It stretches. It becomes something that carries the form of communication, while the substance of it has already dissolved. Eventually, the signal drops below the receiver's threshold. Engineers push the gain higher. They narrow the beam. They run signal processing algorithms that extract coherent data from noise. For a while longer, fragments continue arriving. Pieces of telemetry, compressed images that take hours to reconstruct, a recording of the crew marking an anniversary, the signal so degraded by the time it arrives that the audio is almost unintelligible. And then the analysis team runs the number that everyone has been avoiding looking at directly. At the ship's current velocity and trajectory, the next scheduled transmission burst, sent on the planned schedule from the ship's automated systems, will arrive at Earth in a specific number of years. The number on the screen is longer than most careers, longer than many human lifespans. The receiving array is still pointed in the right direction. The software is still running. The frequency is still being tracked and adjusted. But the data rate is now so low and the signal so faint that a single transmission burst carries less information than a short handwritten note. This is what the end of contact looks like. Not a dramatic cutoff, not a final message, a gradual thinning until the thread is too fine to carry meaning. Mission Control writes a report. The mission is ongoing. The ship is on trajectory. Contact has entered the terminal degradation phase. A skeleton crew of engineers will monitor the receiver indefinitely. And in a conference room somewhere, the next mission review board is already meeting, looking at what was learned, calculating what the next attempt might do differently. The ship is still out there, moving, accelerating, carrying the crew towards something the civilization that launched them will never see. The signal is still coming, faint, getting fainter. It is the most honest transmission humanity has ever sent into the dark. A message that says, we went. We are still going. We are not coming back. Nobody in the mission planning documents calls it that. The official language uses terms like terminal communication phase, one-way mission profile, and permanent deployment. The language is precise and deliberately neutral, the way engineering language tends to be when the thing it describes is too large for ordinary words. What it describes is goodbye, engineered, planned, optimized, and built into the mission architecture from the first design meeting. The crews who board interstellar missions, in any serious planning scenario, will have known from selection. The people who apply will apply knowing. The training will include it. The psychological preparation will center it. The mission culture will be built around a relationship with permanent departure that no human cultural framework has ever been designed to support at this scale. Military deployments involve prolonged separation. Antarctic winterovers involve isolation. Long submarine patrols involve communication blackouts. Astronauts on the space station are separated from their families for months. None of these are permanent. The psychological preparation for all of them relies at some level on the existence of an end date, a return date, a day circled on a calendar somewhere. The interstellar crew has no circled date. Their calendar ends at launch. Researchers who study extreme isolation and one-way commitment scenarios have drawn comparisons to historical populations who knew migration was permanent. The first humans who walked across the land bridge into the Americas had no route back to confirm was still open. The Polynesian navigators who set out across the open Pacific in canoes knew that wind and current made return uncertain. Some populations that crossed specific geographic thresholds in human prehistory made a de facto permanent choice, even without naming it as such. What those populations shared was a relationship with the departure that was communal. The whole group went. The social structure traveled with them. They carried their culture, their relationships, their language, and their institutional knowledge in the same vessel. The departure was not separation from the group. It was the group moving. The interstellar crew carries this template into the mission design. The ship is not a vehicle. It is a community. The crew are not passengers leaving a civilization behind. They are a civilization in transit. small and enclosed, but complete in itself for the duration of the journey. Their bonds are to each other, to the mission, and to a destination none of them have seen. The engineering of this human reality falls to psychologists, sociologists, and mission architects who work alongside the propulsion engineers and materials scientists. Their design problem is how to build a human system that can sustain this for decades, without external input, without course correction from Earth, and without the option of stopping. What they are building, in the most honest description, is a community that has agreed to disappear, to go forward into silence and send back whatever signals can cross the distance, knowing the responses will arrive too late to change anything, and that eventually the signal itself will become too faint to hear. The engineering of goodbye is the part of the mission that never makes the press release. It is the softest and hardest problem in the entire design package. And it points directly to the final question that the physics, the engineering, and the ethics all circle back to, the question that sits at the center of everything this mission represents. There is a version of this problem that does not require a near-light-speed ship to be real. Every hour, the Earth moves roughly 67,000 miles along its path around the galactic center. The entire solar system drifts through the Milky Way at roughly 500,000 miles per hour, relative to the galactic core. The galaxy itself moves toward a gravitational concentration called the Great Attractor at over 1 million miles per hour. Nothing in the universe is sitting still. The solar system you were born in is not where it was when your parents were born. It is millions of miles from that position, in a direction that no spacecraft we have could retrace even in principle, because the rest of the universe has moved too. The Earth of 1,000 years ago is not a location you could visit. It is a coordinate in space-time that no longer aligns with any reachable point in space. You are already, right now, moving at speeds you cannot return from. The civilization you are embedded in is in permanent forward motion through a universe that provides no reverse gear. The Interstellar mission does not introduce this condition. It scales it. It makes it visible. It compresses into the lifetime of a crew and the operational lifespan of a spacecraft. The same permanent departure that the universe has been running on every human being since the species began. Physicists sometimes describe this as the arrow of time problem. Time moves in one direction. Entropy increases. The past is fixed. The future is open. No matter how advanced a civilization becomes, the structure of space-time points every moment, every ship, every signal, every decision, in one direction. Forward. The near-light-speed ship makes this visible in a way that a stationary observer never experiences directly. The crew feels the universe rushing toward them. They watch the sky compress into a ring of light at the bow. They receive the last signal from Earth, and then silence. They carry their moment of departure with them, like an object, a fixed point behind them in space-time that they can measure their distance from, but never return to. In this sense, the interstellar crew is not experiencing something alien to the human condition. They are experiencing the human condition at full resolution. Everyone who has ever lived has been moving away from their past at the speed of time, carrying only memory of what was behind them, with no physical path back. The ship just makes it visible. The mathematics just names what has always been true. What the ship adds is agency. The crew chose to go. They chose the direction. They committed to the velocity. The permanent departure that the universe imposes on every particle is, for this crew, also a decision. And that decision, freely made with full knowledge of the physics, is the thing that separates the interstellar mission from every other kind of permanent departure. They are not leaving, they are going. The distinction matters, and it points to the last thing that physics, for all its precision, cannot calculate. Every equation in this mission has been solved, attempted, or proven insoluble. The rocket equation closed around the fuel problem. Relativity described the time dilation with exact precision. Quantum field theory predicted the Unruh radiation and the vacuum structure. Material science set the thermal and shielding limits. Each number was written down. Each barrier was measured. The math cannot calculate why anyone would go. That is not a gap in the physics. It is a different kind of problem entirely, one that engineering has no tools for and that physics has no framework to address. The decision to accept a one-way mission to train for it, to board the ship, to watch the solar system recede behind you into the compressed ring of relativistic starlight, and to keep going belongs to a category of human behavior that predates the scientific method. Humans have always gone toward the unknown, at costs that the rational calculation did not support. The first humans who left the African continent crossed into environments they had no maps for, carrying no resupply capability, with no established return path. Some of them died. Their descendants mapped a planet. The calculus of the mission, examined before departure, would have said, the risks are too high, the return is uncertain, the fuel in terms of food and water and physical endurance is insufficient for the journey. They went anyway. The Interstellar mission will require, in addition to everything the engineering teams are building, a crew that carries that same willingness. People for whom the destination is worth more than the certainty of return, for whom the permanent departure is a price they have already accepted before the question is formally asked. Mission psychologists who study volunteer populations for high-risk permanent scenarios find that the people who accept such missions are not indifferent to loss. They are not reckless or disconnected from the weight of what they are agreeing to. The research consistently shows they are people who have organized their values around a goal large enough to hold the sacrifice. The mission becomes the frame within which everything else, including return, is evaluated. For the Interstellar crew, the frame is simple and immense at the same time. They are going to find out what is out there. They are the first. Whatever they discover, they will transmit home. And the data that crosses the light years back to Earth will change the civilization they left behind, more than their physical return ever could. They are spending themselves for information, for knowledge, for the expansion of what humanity knows about the universe it lives in. The math says they cannot come back. They are betting that what they find is worth more than the return trip. Whether that bet is correct is not something the equations can settle. It is settled by the people who make it. You are sitting on a planet orbiting a star in the outer arm of a galaxy, among hundreds of billions of galaxies. Your civilization has been spacefaring for less than a century. You have sent small metal objects past the boundary of your star's influence and watched their signals fade. You have pointed telescopes at nearby star systems and found planets orbiting them, some at distances that might support liquid water, some with atmospheric signatures that could mean something or nothing. You have not gone there. You do not yet know how. The physics has described every reason why going there, at any speed that makes the journey humanly viable, is a permanent decision. And you are, as a civilization, still deciding. That decision is not abstract. It is funded by governments and private organizations right now, in research programs studying advanced propulsion, in the design work of mission architecture teams, in the training pipelines of space agencies that think in century-long timescales. The decision is being made slowly, the way civilizational decisions always are, through accumulated investment, through the quiet consensus of researchers who keep working on problems that will not be solved in their lifetimes. The probes you have sent are the opening line of a conversation the rest of the mission must eventually continue. They went one way. They transmitted what they found. They demonstrated that the one-way mission is buildable, operational, and scientifically worthwhile. They are still out there, moving, their signals arriving on Earth as whispers from instruments that launched before most people alive today were born. The next question is when the one-way mission carries a crew. The physics of that question has been answered in full in everything that came before this chapter. The fuel math is clear. The time dilation is exact. The communication blackout is inevitable. The return problem has no solution that current engineering can provide. What remains is the decision itself. A civilization that sends the first crewed interstellar mission is committing something irreplaceable, people, permanently to the dark beyond its reach. It is making a statement that the expansion of knowledge outweighs the guarantee of return, that what lies at the other end of that journey is worth the cost of sending people who will not come home. Every civilization that has survived long enough to ask this question has already answered a version of it many times. Every explorer who departed with uncertain return was the civilization's answer. Every mission that launched, knowing the risk, was the civilization's answer. The Interstellar mission is the same answer. scaled to the mathematics of light years. The ship that eventually goes will carry the crew's best understanding of everything covered in these chapters: the fuel limit, the radiation, the silence, the physics of time dilation, and the certainty that the world they left will not be the world they could ever return to. Even if return were possible, they will carry it all, and they will go anyway, because the question of what is out there has never stopped being asked, and the only answer the universe accepts is the one delivered in person by a crew that boarded a ship, lit the engine, and chose forward. The math says they cannot come back. The mission says they were never going to stop.